This lecture we're going to look at different deposits on Earth's surface and some of their features. We're going to start off by looking at what we call depositional facies. These are generally marine environments. It's essentially where water flows off of continents. This is kind of a cartoon caricature of it. And there's a particular sequence of deposition that nearest the shore, remember, water that's transitioning from land to ocean water is going to be slowing down. As it's slowing down, it's losing its kinetic energy. It's going to be depositing its gravel, the large particles, and it's going to be creating conglomerates, right? If water is transported small fragments of rock and they get deposited first, we would say that the coarsest sediment are closest to the shore. So these would form, they would have the potential of forming conglomerates. So then the next sequence would be the next larger particles that we would get a process of deposition of sandstone. And it continues to get smaller as the water is moving the sediment out toward the ocean. The last things to settle are going to be the shale. And then once you've kind of cleared the water, you get warm, shallow seas that allow for sunlight to reach through. And you're going to be creating limestone. You're going to have photosynthetic organisms like coral reefs and different organisms, photosynthetic organisms that are going to be then forming. So you get this rock sequence of conglomerate, sandstone, shale, and limestone. And this is what we call a depositional facies. It's a sequence of deposition in the formation of sedimentary rocks. Remember, these are detrital, these are detrital, these are detrital with the potential of fossils, and these are chemical. These are the buildup of hard-shelled organisms. And these might also be microscopic organisms. So from land to the deep ocean, we get this conglomerate, sandstone, silt, and limestone. Or excuse me, that should be a shale. I should write that as shale. Sequence. And that's what we're looking at here. So moving on. So here I have what we can start talking about is called a transgression and a regression. A transgression takes place when sea level rises. If sea level rises, we would get this whole depositional facies that shifts to the left. And if it's a regression taking place, we would say sea level lowers, and we would shift this whole sequence or depositional facies to the right. So let's look at what that would look like. Remember, transgressions are rises, regressions are drops. So I can draw this out. And this is a picture I drew on the board, that I get the conglomerate, sandstone, shale, and limestone, right? The potential for coral or hard-shelled organisms that accumulate. So if I call this sea level 1, we're really looking at what happens when sea level rises or drops. So I drew another sequence, right? I get these sediments deposited, and then I have sea level number 2. I say, well, it rises. So then I draw my sediment on top of the pre-existing sediment. The depositional facies stays constant. So I get my conglomerates here, I get my sandstone here that are now over the old conglomerates, I get my shale over the old sandstone, and I get my limestone potential over the old shale. So this sequence of conglomerate, sandstone, shale, and limestone is my depositional facies. It's a very predictable and large-scale sedimentary depositional record. So as global climate changed, so did the depositional facies deposits. If sea level rose, the depositional facies shifted left, and that's what we see here. The same conglomerate, sandstone, shale, limestone, it's just now shifted to the left. And if it dropped, the depositional facies shifts right, and we get this constant predictability of what is deposited out first. So here's where I can do this. So I draw a third sea level, so sea level 3, and notice I had it drop from before. And then I redraw my conglomerates, my sandstone, my shale, and my limestone potential. And now I want you to see what happens if I look at this, and I fast forward through many millions of years, we see these layers as strata, right? Rock layers, sedimentary rock layers. And so now I can start interpreting them. Sandstone would be the oldest based on superposition principle, that if it goes from sandstone to shale, I can interpret this as there was a transgression taking place. Remember, transgression implies that sea level rose. And if it goes from shale to conglomerate, that is a regressive sea or a regression taking place. That the depositional record is also illustrating what was happening with sea level at the time. And it can rise based on the depositional facies, and it can regress or lower based on the depositional record. So once again, I'm looking at the strata, the rock layers that are left behind within the ocean basin. So here I can look at stratigraphy with depositional facies again. That regressions are sea level drops, transgressions are sea level rises, and I drew them in a little different colors. that it's the consistent changing of what's taking place. So if I draw a picture, and if you need to make this larger, but here's what I did. I took this kind of cross section of rock strata out. If I go from shale to conglomerate, I knew that there was a regression. And if I goes from conglomerate to sandstone, I knew that there was a transgression. So I kind of gave you both aspects of that. Here we see a transgression, regression, and here we see a regression, transgression. Okay, both of which reflect climate conditions of an ancient Earth. That it's always the depositional sequence of rocks that change as sea level changes. This marks a change in the global climate. All right, moving on. So let's look at different bedding. That if I look at this picture right here above, I have different sediment compositions of layering. And we just call these just rock strata that have different bedding planes. Right? We see distinctive bedding planes of different sediment. Now, they're all fine, but they can have different compositions. That this could have a little bit of sand in it. This could be mostly clay. This could be silt and clay, back to a little bit of sand, back to clay. And these are just slightly different compositions. Whereas here we call gradation. These are different sizes of particles. We get our coarsest material that settles out first, and it gradually gets finer as we rise up. Remember, as sediment is depositing and being laid down by gravity, often, not always, but the largest, the coarsest particles fall out of suspension first, and that's why we get this gradation. And then we have another sequence and another graded sequence. Then we see bedding planes that differ in sediment size. So gradation is this difference in size. Composition would just be the layers that we get for the different bedding planes. Notice, these are still bedding planes, but these are graded bedding planes. And that's really just based on the size when we talk gradation. Then we can talk graded bedding from turbidity currents. And a turbidity current is an underwater landslide, generally in oceans, that deposit tremendous amounts of sediment. And these sediments are graded, with coarse-grained sediment settling first, followed by smaller sediment. And I see that here. Large, I can actually get some rounded cobble and pebbles, right, gravel-sized sediment. And then by the time I get to the top, I get much finer sands. So here's what happens. You can have sediment that is building up from long-term deposit. It becomes unstable. The suspension then flows down slope. It literally is a large-scale landslide. And the largest sediments deposit out first. And over time, the smaller sediment, the smaller, finer sands and silts and clays settle on top of it. And this is another example of graded bedding. Here we go look at cross bedding. And this is what happens in both marine environments. This is an example of cross bedding in a water environment. And this would be cross bedding in sands from a desert. This would be from wind. So cross bedding here. I want you to observe the direction of the wind or the water flow. The energy transports sediment upslope gently or gradually before it drops off due to gravity, the steeper side. So notice, the gentle side is the windward side, right? In this case, the wind is affecting the gentle slope, and then the steeper slope is the far side. So I can look here, that if I look at this slope right here, I could see that my energy here would have been, the winds would have come from in this case, would have come from the left, and it would have deposited them on the steeper slope is the far side. So the winds for these types of rocks down here, this rock strata that we see in this picture here, well if it was wind, winds would be coming from the left. The steeper side is the far side, remember that. So these are cross bedding, and we find cross bedding pretty regularly in sandstones. And the ripple marks, and last but not least, in rocks we find all these different types of ripple marks. That here on the left side I have what are called symmetrical. That just implies that water might be coming in and might be flowing back. That this would take place. You actually see ripple marks very nicely in Lake Michigan, right along the shoreline. You get equal water in, water out, and that's just from waves crashing. But you get symmetrical. But you get asymmetrical ripple marks when you get a tendency of a current flow. That this would be flowing, let me see these ripple marks. In this case, this is actually from wind. This would be from a desert here. That winds would be blowing from the left to the right. Or this might be on a beach. This looks like a beach. That looks like water right there. Winds would be blowing from the lake and would be blowing these, that would be asymmetrical. And that just tells you there's a constant flow from the left to the right. Whereas up here, these look like it's in a body of water. And this would have been a constant flow from the left or the top left corner to the bottom right. That this is the asymmetrical ripple marks that we see as relic features in sand from either water or wind.